Hi guys, today we're talking about face detection using Detectron2, and this is the first video of the PyTorch or deep learning with PyTorch series. So let's get right into it. So what is face detection? Well, if you take an image such as this one, let's say, of Charlie Chaplin, the great one, and given this image, your task is actually to find the human face in this image if a one exists on the image. So in here, a good result might be something like this. So I'm going to basically show you how you can train a model or use a pre-trained model, fine-tune it using a relatively small data set and basically draw these bounding boxes around the human faces. And why this is useful? Well, basically when you do some sort of face recognition, so if you want to tell who this person actually is for, let's say, security reasons, or maybe you want to detect the emotions of the human face for something like, let's say, marketing or whatever, this task is probably the first step in understanding or solving your problem. So let me just show you a bit more about the Detectron framework, and we're going to basically open a Jupyter notebook or Google Co-op notebook, and I'm going to show you how you can use a small dataset, use a pre-trained model, fine-tune it, and using Detectron2 you will be able to detect faces in like under half an hour or something like that, if you get lucky and get a good video card from the Google Co-op. So what is Detectron2? Well, basically Detectron2 is a state-of-the-art object detection and image segmentation framework done by the Facebook research team. And this is a second iteration of the framework. So this is still like cutting edge alpha technology, and you can have a look at probably the most important places for this framework is actually the GitHub repo. So as you can see, the development is really active, and yeah, almost every day there are a few commits in here. But I've been using Detectron2 for the past maybe a month or even more, and I could say that it's well, relatively stable and extremely easy to use even for a newbie like myself. So let's get right into it. And as you can see, this is the power of Detectron2. It does object detection, image segmentation, and it does some pose estimation of the people. So this is pretty cool. It has a lot of pre-trained models called the Detectron2 Model Zoo and baseline models. And as you can see, there are models based on the Coco object detection dataset trained on, I believe, ImageNet. Let me see. Yeah, we have ImageNet pre-trained models in here, and we have some models based on the Cityscapes dataset. But yeah, extreme variety of pre-trained models, and I'm going to show you how you can use one of those. Actually, I believe it's probably this one. Yeah, but we will have a look at it. So the next thing that we're going to need for the object detection part, and basically face detection is just object detection of one particular thing, and this particular thing is the human face. So the next thing that we're going to show to need is to have some sort of data set with human faces, and lucky for us, we have the Dataturks dataset, a dataset provided by Dataturks, face detection in images, and it's a pretty old dataset, and it has about 500 images, which is a really small dataset. But on those images we have around 1.1k faces tagged manually, And as you can see, we have the images and we have the bounding boxes around the human faces in here or in here. If you actually open the URL from the Kaggle, you can see that this has been completed. And here are some examples. You should take a look at this one in particular, because you can obviously see that there are some annotations that are missing. So this the quality of this dataset might not be perfect, but still we'll use it to train our model. Let's have a look at another example. Okay, so some sort of movie poster or a book maybe. And the next one, yep, multiple faces. This one is good actually. And these images look like they're taken from some sort of movies or whatever. Okay, so these are good, and I hope that most of the labels are pretty good as well. So given that we have the data and the framework that we can use for detecting human faces, we can actually start and open a notebook and start coding, I guess. So the last thing that I forgot to mention probably is that Detectron is actually built on top of PyTorch, but the way that you use Detectron is like you don't even know that PyTorch is used under the hood. So Detectron2 is actually a very well abstracted framework for object detection and image segmentation. I don't really think that there will be a backend that is based on TensorFlow or Keras or whatever, but yeah, just keep in mind that actually the backend is written in PyTorch, and the code is actually the code of Detectron2 is actually really readable, and you can just dive into the GitHub repo and probably understand what is happening and when it's happening. Is this package Detectron2? And yeah, they're based on features, so it's pretty well structured project in my opinion, at least. Okay, so the last thing that I'm going to mention for Detectron2 is that there is a blog post, a Google Colab notebook, and a getting started document. This blog post is well, relatively old in deep learning history, like timeline, but it shows the power of the initial project, and it's really powerful. There are some improvements in here. Detectron2 is actually training really fast compared, well, training a model with Detectron2 is really fast compared to Detectron1 or other frameworks, and there's a benchmark for that. You can see this one in here. The documentation for Detectron2 is on the readthedocs.io, but it's relatively, let's say, sparse at the moment. There are some good insights you can get from here, but mostly I believe you should go and, at least for now, check the source code. There's a getting started guide. One, you can use a pre-trained model, and there is a Detectron2 beginners tutorial, which is really good, and it shows all the steps for training on a custom data set, finding balloons in images, which is really similar to what we are doing in here actually. So yeah, go and have a look at those. They're good starting points for understanding Detectron2. And this tutorial is just a tiny bit more complex because yeah, we need to do some pre-processing on the face detection data. Okay, so let me start with opening the Colab notebook. I'll reconnect because obviously we were disconnected. And let's start by having a look what GPU did we got assigned, because that's really important. Okay, so we have the P100, so we're really lucky in that regard. And I'm going to start installing the dependencies for the Detectron2. And the next thing that I'm going to do in here is actually to clone the repo and install the Detectron2 project. After the installation is complete, we are going to have to restart the runtime because Detectron2 is we won't be able to import the libraries unless the runtime is restarted. And let me dive in a bit into the imports. As you can see, we have pretty much the standard stuff. I know those imports are like really large, but I don't care. I just import everything and start experimenting from there. Some of those might not be used today, but yeah, that's life. So we have most of the Detectron2 imports. You can see that we have a default predictor, default trainer, a visualizer, a dataset catalog, some evaluator, and the model zoo actually, where we can which we can use to get the model config file and the model pre-trained weights, and I'm going to dive a bit deeper into that later on. We have Seaborn, the plotting stuff, and seeding, NumPy, and Torch in here. Okay, so while this is training, I'm going to go to the Kaggle again and have a look at the data itself. And as you can see, the data itself is just a JSON file, and this JSON file actually contains a content, which is, let me open this up for you, which is an URL to an image that is contained in the dataset. So we have to go on and download each image, and as you can see, those images are hosted on S3, so on Amazon Web Services, which is great. And we have annotations, and the annotations contain actually the bounding boxes for the human faces, and they have points x and y, so x min, y min, x max, y max. We have the image width, image height, and then another annotation. So for this image, you can see that there actually should be 3 faces, but yeah, probably the annotators annotated this face and this face in here as well. So that's just my guess based on the annotations. So we basically have to download each image locally on the Google Co-op runtime, and then convert the annotations to a format that is understandable by Detectron2. So yeah, the next thing that I did actually was to upload this same JSON file, face detection.json, to my Google Drive, so it is available as a G-download, so you don't have to actually go to Kaggle and download the JSON file and probably upload it into the Google Co-op thingy. Okay, so this is taking a bit of time, I guess. So let me pause this. So now that the installation of Detectron2 is complete, we can go ahead and restart the runtime. Okay, and then actually do the imports and download the JSON file. And the next thing that I'm going to do is to load the JSON file into a pandas data frame. But if I do just this, we're going to get an error, and this is based on because of the format. Sorry, I haven't included the file name correctly, but yeah, we have trailing data. So if I go ahead and just hit this, we can see the first couple of lines of the JSON file, and as you can see, each line is basically just another JSON object in here. And fortunately, we can use the lines through argument in here to load each line into a pandas row. So let's have a look at this. What do we have here? And yeah, as you can see, we have the content, the annotation, which is really not well parsed, and we have something called extras, which I'm not going to talk about because I believe every extra is not a number. So yeah, we have a bit work to do. We have to do some pre-processing to extract the data from here into a format that is understandable even by us and Detectron2 probably. Recall that we have to actually download these images, and to do that I'm going to start with creating a folder called faces, and in here I'm going to download every image and name it and rename it because those names are kinda insane. After we download each image, I'm going to record every image's height, width, and I'm going to parse the annotations. So each annotation or each face annotation is going to get a single line into a data frame that I'm going to create right now. And if you don't know or you don't understand what I'm talking about, let me just show you the code for that, and we can after that review the resulting data frame, so it might get a bit clearer. Let me just start by iterating over each face or each example into the faces data frame, and I'm going to start actually by creating a dataset list, and next I'm going to iterate over each example, and I'm going to use TQDM to follow the progress. And actually right now TQDM won't work as expected, so you have to specify the total number of items that you have, and this is just the number of rows into the data frame. So if I go like this, you can see that TQDM is working properly. So let's start by downloading the image from the URL, and I'm going to use URL lib request for this. And in the row the column is content, so I'm going to take that. I'm going to convert this into an image using PIL, and I'm going to convert that to RGB image. Okay, so now we have the image data in the image variable stored, and then I'm going to specify the new name of the image, and this is going to be basically the faces folder. This is going to be face underscore the current index dot JPEG. So this will be the new name of the image, and I'm going to save this into the faces folder. And I'm going to specify the format, which will be JPEG. Okay, so next I'm going to take the annotations, and as you can see those are actually an array or a list, so I'm going to iterate over those. And for each one I'm going to create a new data row which we are going to store to the dataset at the end. And in here I'm going to specify a couple of things. First, I'm going to take the image width, then I'm going to take the image height, and I'm going to take the points. The points are actually the annotated points at which the bounding boxes should lie. And this, let me just show the example again. We have the minimum points and the maximum points, And as you can see, those are actually fractions. Those are fractions of the image width and image height. So you have to actually get the real coordinates, we're going to have to multiply by those numbers, and I'm going to show you how you can do that in a bit, which is not hard at all, let's be honest. Let's take the points now. And I'm going to start to preview the data row. We are going to preview the file name, which is going to be just the image name, preview the width, preview the height, then I'm going to calculate the x-min, and this is just going to be the, let me just go to the example again. This is going to be the first point or the 0th index, and I'm going to take the x value in here, and I'm going to multiply that by the width. So this will be the absolute coordinates of the x-min. Okay, so this looks like points, 0th element for the minimum elements, and I'm going to take the x and I'm going to multiply that by the width. Okay, so we again we can just leave it in here, but this should just be an integer, and I'm going to round that, so I'm going to convert it to an int, round it, and this should be it. I'm going to do this exactly the same thing for the y-min, and I'm going to multiply that by the height. Okay, so we have the x-min and y-min. Then we are going to do exactly the same thing for the max coordinates, x-max and y-max, but I'm going to take the next element from the points, and again this will be these two items. Okay, so now we have the x-min, y-min, x-max, y-max. The final thing that we need for this is actually the class. We can have multiple classes. For example, you can try to detect maybe human faces and cat faces, and those should be two separate classes, but for our example we just have a single class which we will call just face. Okay, so now we just run this, and as you can see this can take a bit of time, and I'm going to again pause this video in here. Okay, so the dataset is now downloaded and converted into everything that we need, and I'm going to show you the folder in here with the faces. This might take a little bit of time, but yeah, we have the images, and I can show you actually the first image that we had. So yeah, we have it in here on the local Google Colab machine. Now that's great, but we just have the dataset as a list, and I'm going to convert this into a data frame. And I'm going to show you what is the final result. And as you can see, we have, for example, the face 0, the first image that we have, and in there we have the two annotations for the faces with different coordinates for the x-min, y-min, x-max and y-max. So yeah, this should give you a rough idea of what the final result is. Okay, so that's great. And the next thing that I'm going to do is to have a look at the unique files that we have. So what is the size of our dataset? How many images do we have? And the total amount of rows. Okay, so we have only 410 images, which is way less than the one that they told us, 500, and we have actually a bit more annotated faces. So that's quite alright. So let's have a look at a simple annotated image, and to do that I'm going to copy and paste some code in the name of time, saving time, and I'm not going to go through this source code. You can do that on your own, but let me just start by selecting an image. And I'm going to just take the first image, annotations. I'm going to annotate it. Disable the resizing, and I'm going to use PyPlot to show it and turn the axis off. So this again will be the first image. And yeah, as you can see, we have the faces annotated at probably the right places. So the dataset should be alright. Let me just show you the next one. Okay, so we have another face in here. This looks good. And let's just do another one. Okay, so this is pretty interesting. I mean, look at how the horse is looking at those guys. Okay, final one. Okay, so in here you can see that again a lot of annotations are actually missing around this guy's face, and there are a lot of faces in here that weren't annotated. So this is basically the real world. Sometimes the annotations are missing, and your model will probably try to do its best, but yeah, given that your data is not as high quality as it can be, you can't really expect that your model is going to do a perfect job. So when you prepare your own datasets, be aware that you might want to have a high quality data. Okay, so the next thing that I'm going to do is to start preparing the data for Detectron2. So let me just mark this in here, face detection with Detectron2. Okay, so we had a look at the annotations, at the images, and the next thing that we are going to do is to get a training data set and a test data set. So I'm going to split the data, but the splitting itself won't be using the train test split from scikit-learn. Why? Because we have we can have a couple of rows that are annotated for a single image. So if we split the data, you might end up with rows for the same image in the training and the test set. So we're going to avoid that. And let me just start by getting the unique files. And then I'm going to take the train files, and I'm going to use NumPy random choice. I'm going to take some random files from here, and the amount of random files that I'm going to take will be actually 95% of the data. So I'm going to take the length of all files, and I'm going to multiply that by 0.95, and I don't want to sample with the replacement, so this should actually get the train files. Let me just check those. Let me have a look at the first 10. Yeah, we have a set. Okay, so they are just some file names. Okay, so the next thing that I'm going to do is to take the training files from the whole dataset, and I'm going to do that by using file name isin, these are the training files, and the test files are going to be the files that are not into the train files, and I'm going to do that using the tilde command. So this is negation basically. Okay, so let's have a look at the train df shape and test df shape, if I can write properly. So, whoa, that's a bit strange. Sorry, I had an error in here. I don't want to replace the files actually. So, yep. Alright, that's more like it. We have the training data, we have a lot of examples in here, and we have only 54 annotations for the testing. So we can continue with this. And then again, I'm going to take the classes, which we only have one. But this is just some generic code that you can use as well when you have multiple classes in here. So you might train this with multiple classes. The next thing that I'm going to do is to define a constant called images path. And I'm going to say just faces, because this is the folder that we've created, this one, faces. Okay, so the next thing that I'm going to do is to create the dictionaries that are required by the Detectron2 framework, which is going to, this will be just a function that takes this data frame and converts it into a format that is suitable for Detectron2. And this is another, or the final pre-processing step. So let's just go ahead and do that. I'm going to define the function called create dataset dicts, and I'm going to pass in a data frame and the classes that we have. I'm going to basically iterate again over all unique files into the data frame. And for each file, I'm going to create a record. Each record is going to contain the coordinates of the bounding box, some sort of segmentation, which I'm going to explain in a bit, and the category ID, which is basically the class ID of this example. So let's start by just filtering the file name of the image. So let me just show you this one again. We are going to filter all the rows that contain the current file name. So for example, the first one, we're going to take those two rows. This will be contained into the image.df in here. And I'm going to create the file path, which is going to be the images path. And I'm going to start filling up the record dictionary. File name, file path, image ID. And Detectron2 requires that each image has its unique ID, and in our case this will be just the index of the unique file. We have to record the height and width of the image, and I'm going to take the height in here, just on the first element. Recall that each element will have the same width and height. And then for each record, I'm going to specify the actual annotations. So for each image, we will have a single record, and each annotation in this record will contain annotations, which are going to be the actual phase bounding boxes. So let's start by creating a list for that. And I'm going to iterate over all of the rows in the image. So each row will be an annotation. And I'm going to take all the elements in here. Let me just do this. So xmin, ymin, xmax, ymax, this should be it. And I'm going to create a polygon that will be the segmentation part, which is going to match at 100% the bounding box of the image, of the annotation. And the this should be the xmin, ymin. So this polygon, for it we're going to specify the 4 different points at which it is defined, and this will be the top left, top right, bottom left and bottom right, basically. And I'm going to use iter tools to create a chain of points for this polygon. Finally, I'm going to create an object that will represent a single annotation. I'm going to specify xmin, ymin, xmax, ymax in here. And I'm going to specify the mode, and the mode is going to be xy, xy, absolute coordinates. Of course, you can use another bounding box mode, but you have to do those coordinates according to this mode. And the segmentation part is going to be just the poly. And the category ID is going to be the index of the class. And isCrowd is going to be false. This is a parameter that I believe is used for detecting objects in large amounts of possible objects or something like that. We are not doing anything like that in here. And I'm going to append the annotation to the objects list. Finally, after the for each loop is complete, I'm going to append the annotations to the record. And I'm going to finally dataset dicts, I'm going to append to it the record itself. And at the end of the function, I'm going to return the dataset dicts. So this should be it, except that I've missed a comma in here. Yeah, so this should be it. And as you can see, this is a pretty large chunk of code. But yeah, this is the format that we are going to use for the Detectron2 datasets. Okay, so the next thing that we're going to do is to register the dataset that we have. So Detectron2 has a catalog of datasets and metadata, and in here I'm going to register 2 new datasets. one for the training dataset and one for the validation dataset. So to do that, I'm going to iterate over a simple array, which is going to be the train and the validation data sets. And I'm going to use the dataset catalog register. I'm going to register faces D, so this will be train or validation. And a lambda function in here is going to be the name of the current train or validation dataset. And in here I'm actually going to call the create dataset dicts. Okay, so this is going to be the train df if d is equal to train, otherwise is going to be the test df, and the classes will be just the classes. Okay, so we have the dataset catalog register complete, and then we have the metadata catalog. So in here I'm going to say faces underscore d again, and in here I'm going to set thing classes, so what are all the classes that we are looking for, and I'm going to say that we have the classes from here, which is again just the faces. Okay, so we have registered the datasets, and the metadata knows about the classes that we have, and then faces metadata is going to be the metadata catalog get faces train. So this should be it. Let me run this. Okay, this should be working now. So we've registered the datasets, the metadata catalog, and we have the metadata in here as a variable. The next thing that I'm going to do is copy and paste our custom trainer, which will basically help us evaluate the model while we are training the model detection, the face detection model. And I'm not going to go into a bit details in here. There is much more details on that in the blog post that I'm going to link, as well as the source code. So let me start by finally looking at some Detectron2 code, and we are going to start by configuring our model, and this will be much different compared to what you might be used to when working with let's say PyTorch or Keras or TensorFlow. In here we just creating a config file, and then we are having a look at the models from the model zoo. And actually in here I'm going to have a look at the mask RCNN, this one from here. And as you can see, it has a lot of time to train and it requires a lot of memory, but its average precision is really high, and the mask or the segmentation mask average precision is high too. There are a lot of other models in here that you can choose from, but this one seems to be performing really well, and it's available. So I'm going to take just the config files that I've already prepared so I don't make a typo. So these are these ones. So instance segmentation, mask RCNN, and this big model that we've talked about. And as you can see, I'm getting the config file from the model zoo, and I'm getting the checkpoint URL from the model zoo as well. So first the config file and then the weights. So this is just great. And then I'm going to specify the data set that we're going to use for training and testing. And for testing, I'm going to use faces val for validation. And I'm going to specify the number of workers that are going to be basically the threads that award the images. So this should be fine too. And the next thing that I'm going to show you is how you can configure your solver or the optimizer in here. So the optimizer contains the regular stuff like warning rate, maybe the maximum number of iterations and the batch size, but there are a bit more configurable compared to, let's say, Classical, PyTorch if you're using Adam or something like that. And I'm going to show you how you can configure this one. So let's start with the batch size. And I'm going to specify 4 in here. And this, you might try to increase this when you have more GPU memory, but it might be advisable to have relatively small batch size. The next thing I am going to specify is the base warning rate, base LR, and this is going to be 001. So this is pretty standard initial warning rate. The next thing that I found a bit interesting was the warm-up iters or warm-up iterations, and I'm going to specify 1K for this one. So let me just specify the max iterations and specify the steps and yeah, let me just go through this. We have a maximum number of iterations 1.5k. For the first 1k of those, we are going to warm up our solver. So our solver will basically go from warning rate of 0 and progress to the warning rate that is the base warning rate. And at step 1000, just as the iterations are at this point, that's a bit dumb configuration, I guess. The solver will reduce the warning rate or divide by this number. So basically we will get a much smaller rate into the 1K and 1.5K range. So let's execute this. And now we're going to configure the model itself. This will be specific to the model that you've chosen, but in here you can specify the batch size per image, and you can, this is really important, you can specify the number of classes that this model should classify. Roy heads num classes, and this will be the number of classes that we have in here. The final config is going to be at how many steps we are going to evaluate the performance of our model. And if I go to the documentation and go to the use configs and go to the config references, you can see that this is probably each possible config file, config setting that you can set. And there are really a lot of those. So if you go, for example, to the model Roy heads batch size per image, let's say, number of region of interests, total number of regions of interest per training mini batch. So this is how this is calculated. So the default value is 512, and this is basically multiplied by the images per batch. So in our case we have let's see, 64, and we're going to multiply that by by 4. So this will be 256 we'll have for these regions of interest per training mini batch. Okay, so I didn't know that. This is pretty interesting setting. Okay, so we have the configuration in here pretty much done, and I'm going to specify an output directory. Which is the by default output, and I'm going to create a trainer, and it's going to accept the config file. I'm going to say to the trainer resume or what, and I'm going to specify resume false, and then I'm going to call the trainer.train, and this should hopefully start the process of training using your own dataset. So this might take actually a lot of time, but the GPU, the Google Co-op instance is really fast, and as you can see, it already loaded the images. We have 388 images only with this many annotations, and the first thing that it's going to do is to go ahead and download the model if you haven't downloaded it already. So as you can see, another thing that it does is applies some transformations in here. It does random flipping and some resizing. Oh, we have an error. So I made an error somewhere. Let me pause this. So there were a couple of errors in here. I forgot to replace this with width, and in here I set image df, which is strange. So I'll have to reset the runtime and redo the imports, and actually went ahead and saved the annotations to a local CSV file, so I don't have to do all of the pre-processing again and wait for it. So let's start by running all of this and starting the training process. Okay, and hopefully this should work out. Starting training from iteration 0. So yep, this should start the whole thing, but let's wait and see if this is going to work out. In the meantime, I'm going to tell you that actually I went ahead, trained a model for about 2 hours on Google Co-op and saved a pre-trained model. So this pre-trained model we are going to be able to now download from Google Drive. And yeah, as you can see, yeah, this is even actually faster with the P100. And I'm going to go ahead and interrupt the runtime. Okay, so I'll go ahead and download the pre-trained model from Google Drive, and I'm going to store it into the output model final, and this will be just a checkpoint. I'll have to wait for this, and as you can see, this is a pretty large model, the pre-trained one, that is. Okay, so this is the model, and the next thing that I'm going to do is to change the model weights to point to the pre-trained model. this should load the model, and then I'm going to specify a threshold at which the model will make a decision. So we want to be this certain, or right about 85% certainty into the prediction, and only then the model will make the prediction. And I'm going to instantiate a default predictor using the config file. This should do the walling, and we have the predictor. Okay, so I'm going to basically skip this and show you just the result of that. This will basically use the model, use the faces validation dataset that we have, and do some inference on top of that, and just spew out the results that we have into in here. So how do we evaluate those object detection models? Well, as you may already know, the most important metric in here is actually IOU, or this is let me just go ahead and show you the formula for that. This is the intersection over union, which is the area of overlap and the area of union. And if you don't know what I'm talking about, there is a really great article on Medium posted by the one and only Jonathan. Yeah, you can see his name, I guess. And here is a very good example of what IOU is. So we basically have the ground truth, or the annotation made by the human probably, and the predicted annotation, and we have the area of overlap. So this will be this area right here, and as you can see, this is the one over here, and the union, or the area that is covered by both or either one. So this will be the much larger area, and this should give you a number that is between 0 and 1. So the greater the overlap, or so the greater the predicted and the ground truth area that is combined together, the closer the number is going to be to 1. And you can see, and you can use that to set some threshold, calculate precision and recall based on that, and you can get some pretty good average precision metrics and all of that using it. So this is just a whirlwind tour of how object detection models are evaluated, and you can go ahead and read this great article to get a better understanding of what of how you can evaluate object detection models. So let's do something to show us what are the results based on the model. I'm going to take all of the test images, and for each one make this, sorry, and for each image I'm going to take the file path to the image, read the image using OpenCV, get the outputs of the predictor of our model, and do a visualization using the visualizer class. And in here I'm going to do some color pre-processing, set the metadata. We have face metadata, specify the scale. We have a full scale image, and instance mode, color mode image. So we will just get a nice image with the colors. Then I'm going to take the instances or the predictions, go put them on the CPU, and basically remove the segmentation masks. Because if you recall that our model is also image segmentation model, but we are just using it for object detection. Then I'm going to draw the actual predictions on top of the image, get the resulting image, again do the same color augmentation, get the file name of the image, and use OpenCV to write the image into the annotated results, file name, and write the result in there. So let's just do this, and this is running our model on the testing data that we have. So this is now complete, and I can open an image, and hopefully this should be alright. Yeah, this is the image from the beginning of the tutorial, and as you can see, it detected it as a face. And in here you can see a lot of faces were detected, but one of the errors in here, actually we have two errors. We have face within face detection, so this might be negotiated by choosing a different threshold, but yeah, applying a threshold for face detection is a really interesting problem. But as you can see, the model over detected in here. So in here we have two missing faces and another over detection. In here again, some of the faces were detected. I don't see any, maybe, I'm not sure, no over detection in here, but some of the faces are missing. Okay, so in here we have probably correct. Yeah, this looks really good actually. Okay, so this one it did quite well, but yeah, okay. So in here again, very good. And recall that we are using just under 400 images are examples to train this model, and this is actually very good when using a pre-trained model on ImageNet. And just for the fun of it, let's take another image that is not anywhere on this dataset, and let's say person. Okay, let's probably take this girl. Let's remove the annotated results. And let's upload the image of the girl. This might take some time because the image is 10 megabytes. I'll pause the video. Okay, so the image is in Google Co-op, and I'll rename it to, let's say, girl.jpg or whatever. I made a typo. Girl. Okay. So I'm going to take all of this. Let me just do this, and I'm going to take this in here, paste it, specify the file path as girl.jpg, run this, and open the annotated results. Let's download the image actually, so it will be a bit better to understand it. And again, I'm going to pause the video. Okay, so the image is downloaded, and I'm going to show you the result. And this is the result. So yeah, our face detector is actually quite good. And keep in mind that this image is actually really large. So yeah, this is the dimensions of the image, and our model was able to use this really large image and detect the face, I would say, very well. So this is pretty much it for the tutorial on face detection. Again, you can use this pre-trained model as a first step in detecting faces, or when you want to do something like face recognition, understanding human expressions, reading smiles, let's say emotions from the person, or for some security reasons, however you want to use this one. And there are a lot of pre-trained face detectors, but you can basically use Detectron or some similar framework to create your own or build your own custom dataset and train on it using a framework like Detectron. So I'll link the complete source code, complete tutorial down in the description. Please like, share, subscribe, and I'll see you in the next one. Bye bye.